The workers in their early 20s move slowly around the landing gear, and every action inside the clean environment unfolds with almost absolute precision. The soft sound of metal tools touching the aircraft structure echoes quietly through the calm atmosphere, making the entire hangar feel more like a laboratory. The aircraft is still relatively new, and the engines operate normally, yet the maintenance team still spends hours simply trying to reach a wide. That moment becomes the beginning of a larger question inside the quiet maintenance hangar, asking why the future of aerospace engineering now begins by male engineer in his late 20s realizes that a beautiful design is not always a design that can be maintained efficiently over decades of operation. The workers in their early 20s continue removing layers of protective panels inside the technical bay, while time passes faster than the maintenance process itself.
Every minute the aircraft remains parked inside the hangar means higher operational costs, disrupted flight schedule, and invisible pressure spreading throughout the entire.
Inside the clean, silent, and disciplined workspace, the question is no longer how to build a more powerful aircraft, but how to maintain.
Under normal operating conditions, the matte gray narrow-body aircraft is designed to perform thousands of continuous flights with an extremely high level of reliability.
The female engineer in her early 20s checks engine temperature data after every flight, while the workers in their early 20s clean the technical surfaces around the landing gear area. Every internal system inside the aircraft, from hydraulics and electronics to pressurization and fuel distribution, must function simultaneously. In the past, many aircraft designs focused almost entirely on flight performance, fuel efficiency, and aerodynamic optimization, as a result, maintenance teams often had to remove multiple structural layers simply to replace a small component hidden deep inside the aircraft systems. Sometimes, disassembly takes longer than the actual repair itself.
The workers in their early 20s must use multiple specialized tools just to reach difficult technical locations, while the aircraft remains.
In an ideal situation, a good aircraft should not only fly efficiently, but should also allow maintenance crews to quickly access every area that requires routine inspection.
The female engineer in her early 20s opens a new structural simulation on the technical display and demonstrates how modern access panels are.
That is the foundation of a new engineering mindset in which maintenance is no longer treated as a stage that comes after design, but instead becomes a central part of the design itself from the very beginning. But the conflict begins to emerge when engineers realize that a structure optimized for aerodynamics is not always optimized for maintenance during daily operations. The engineer points towards several locations that remain extremely difficult to access, despite requiring frequent inspections. The workers in their early 20s must work in uncomfortable positions between narrow structural sections simply to replace a sensor no larger than a human hand. Every time too many structural layers must be removed, the risk of secondary errors increases, inspection time expands, and the aircraft remains.
Wondering why a component that frequently requires replacement would ever be installed in such an inaccessible location.
That contradiction becomes even clearer as the number of electronic systems inside modern aircraft continues increasing rapidly. The more advanced an aircraft becomes, the more complicated maintenance can be. New technology improves performance but creates additional layers requiring constant monitoring.
The engineer understands that the future of aviation will no longer tolerate designs that force maintenance procedures to take excessive amounts of time.
An aircraft that saves only a small percentage of fuel but requires many additional hours of maintenance every week will eventually become an inefficient choice in real-world operations.
That is the moment when the entire engineering team inside the clean and silent hangar realizes that the biggest question of the future is no longer how fast an aircraft can fly. The core answer begins with completely changing the design philosophy inside modern aerospace engineering.
Future aircraft will be built with maintenance accessibility as a priority, meaning that every critical system must be positioned where technicians can reach it as easily as possible.
This approach not only reduces repair time, but also lowers the possibility of errors caused by removing unnecessary structural layers during maintenance procedures. We're showing how electronic assemblies are grouped into modular sections that can be replaced almost like exchanging an entire functional block. The workers in their early 20s no longer need to remove large sections of panels like before, and instead only access the exact maintenance zones prepared for routine servicing. This mindset changes the entire structure of aircraft design, because engineers must now think about the maintenance crew from areas requiring frequent inspection are positioned near quick access panels, while intelligent sensor systems automatically send warnings before failures actually appear. This is the predictive maintenance graphic I mentioned. It highlights potential issues before they cause failure.
Excellent. Let's brief the team on the replacement modules. That means maintenance is shifting away from repairing failures after they happen and moving toward predicting and preventing failures before they begin.
When comparing the old engineering mindset with the new one, the greatest difference is not found in materials or engines, but in how engineers view the real operational life. Under the old mindset, maintenance was often treated as the responsibility of technicians after the aircraft completed its design phase and entered commercial operation. Under the new mindset, maintenance becomes a central part of the design itself, standing equally beside aerodynamics, fuel efficiency, and structural stability.
The female engineer in her early 20s compares two design layouts and explains that moving a system assembly only a few centimeters can reduce many hours of maintenance every month.
The workers in their early 20s no longer need to crawl deep into narrow and dark compartments because they can now work directly through standardized quick access panels. This change not only saves time, but also reduces exhaustion, minimizes human error, and significantly improves safety throughout the entire maintenance process. Maintenance-friendly design is not a sacrifice of performance, but a method for extending the operational efficiency of the entire aircraft across decades of continuous use. An aircraft that is difficult to repair may look highly advanced on paper, but in real-world operation it eventually becomes a costly burden for the entire aviation system behind the. In contrast, an aircraft designed with maintenance as a priority will always return to the skies faster, more reliably, and with fewer risks after every technical inspection. That is why the future of aviation is shifting away from the mindset of simply building machines and moving toward the mindset of sustaining continuous operational readiness. Inside the clean and silent maintenance hangar behind the terminal, the female engineer in her early 20s closes the final inspection panel.
The Middle Eastern male engineer in his late 20s watches the matte gray narrow-body aircraft preparing to return to the taxiway and
The workers in their early 20s organize their tools within an atmosphere of absolute discipline, where every minute saved carries enormous importance.
Future aircraft must be designed with maintenance as a priority, since continuous operational availability is what ultimately determines the true value of a modern flying machine.
An aircraft that only looks impressive when leaving the factory will never remain successful for long if it forces maintenance crews to waste excessive time and accept unnecessary risks during every inspection.
The engineering mindset of the future therefore no longer focuses on creating complexity simply to impress people, but instead
That final moment reveals that the future of aerospace engineering does not depend on how difficult humans can make machines. The future of aviation will no longer be defined only by speed or engine power, but by the ability to maintain stable operation throughout decades of continuous technical service. A truly modern aircraft is not the aircraft that is the most difficult to build, but the aircraft that can be maintained most easily, most safely.